This is topic 1, video 6. In this video, we're going to talk about the difference between empirical and molecular formula, learn how to convert between percent composition to empirical formula, and be able to understand what combustion analysis entails when we're given lab data. Okay, so first let's talk about what the empirical and molecular formulas are. Empirical formula is going to be the simplest whole number ratio of an atom, whereas the molecular formula is the actual number of atoms, each element present in the molecule. So for example, let's say our molecular formula was C4H10. The empirical formula is the reduced version of that. So you want to see what number can go into each one. So we could divide this by 2. So our empirical formula would be C2H5. This is empirical because there's no way to reduce this further. There is no number that goes into both 2 and 5 that we could use to simplify this. We need to be able to figure out what the molecular formula of a compound is when we're given just the empirical formula and molar mass. So what would we do with this type of problem? Let's look. So a compound has an empirical formula of CH2 and its molecular mass is 42.09. Now we have to figure out what the molecular formula is. So if the empirical formula is CH2, what we're going to do is add that up. So go to your data booklet, look up the value of CH2 to find the relative molecular mass. We get 14.03. You take the big one, the molecular mass, that's the larger one. You divide it by what the empirical formula weighs, 14.03, and you get 3. So that means that the molecular formula is 3 times bigger. So then you're going to go back to your empirical formula and distribute your 3 in. That would be C3H6. Next, we want to look at how you determine the empirical molecular formula for percent composition data. So when you're given the percent composition, since the values will always add up to 100, we're going to make them grams. The first step is going to be to convert them into moles. So we're given a problem where we're given 20% hydrogen, 80% carbon. So first step is going to be to convert the percentage of hydrogen into moles and to convert the percentage of carbon into moles. So let's look at what we have. We have 80 grams, we're saying, of carbon divided by 12.01, coming from your data booklet for carbon's mass, and 20 divided by 1.01, which is 20. The next step, after we converted each one to moles, is divide by the least number of moles. So we look at our moles. We have 6.67 and 20. Well, what's smaller? That's easy, 6.67. So we're going to divide each one by 6.67. So that means 1 for carbon and 3 for hydrogen. So when we write out the formula, we write there's 1 carbon and 3 H's. But that's not all, because they don't want to know just the empirical formula. They also want to know what the molecular formula is. So then we're going to repeat what we just did in the previous slide, where we add up the mass of the empirical formula. So you go to your reference table and find out how much that weighs. We add that all up. And now we're going to divide our molecular formula mass, which is 30.08, that was given to us in the problem, how much the big one weighs, divided by the little one, the empirical formula, and we get 2. So that means the molecular formula is 2 times bigger. Since we found the empirical formula to be CH3, we distribute the 2 in, we get C2H6. Okay, here's another example. They give us the percentage of carbon, nitrogen, and hydrogen, as well as the molar mass. So what we do is, first step, we're going to go to moles. So you take the 62.5 grams of carbon, convert it to moles, you get 5.20. 8.4 grams of hydrogen, convert it to moles, and the same thing for nitrogen. Okay, after we figured out the number of moles, then we're going to divide by the least number of moles. So since the smallest number of the number of moles is 2.8, we divide each one by 2.8, and then that would give us 2.5 carbon, 4 hydrogens, and 1 nitrogen. But you see, we can't leave it as a decimal, so if you have a fraction or a decimal, you're going to multiply it by a whole number, whatever it will be, to get you to, actually a number that will get you to a whole number. So we multiply each one by 2. So our empirical formula is C5H8 and 2. To figure out what the molecular formula is, you add up and find the mass of the empirical formula. And they give you the molecular formula mass in the problem. So you do molecular formula mass over empirical formula mass, and you get 3, and then you distribute that in. Next, what we want to do is take what we just learned about calculations of empirical formula and molecular formulas and apply them to a real-life lab situation. In 10th grade, you take a strip of magnesium metal and you put it into the flame of a Bunsen burner. And what happens is you see this bright white light. We tell you not to look into it. But what happens is the magnesium strip reacts with oxygen in the flame and we form magnesium oxide. So the goal of this little experiment right now, what we're going to do is try to figure out, well, if we started with magnesium, we added oxygen from the flame, and then you form magnesium oxide. That's pretty much, after you burn it, you'll see that if we were to put it into a crucible dish, that's what would be left, the magnesium oxide. So we're going to assume that the increase in mass is all due to the oxygen that it combined with in the flame. So here's some empirical data that we were given. You have the crucible and lid. Then you take the crucible and lid and you weigh it with the magnesium before the reaction. Then you take the magnesium and you stick it in the flame. And you weigh again the crucible, the lid, and now the white solid after the reaction has occurred. If we want to find how much or how many moles of magnesium, what we would do is take your crucible, lid, and magnesium, which is the 19.820, and subtract the 19.777. That will give us grams of magnesium. So crucible, lid, and magnesium minus crucible and lid equals magnesium. Then you're going to convert that to moles, and you get 0.001 moles of magnesium. To find how much oxygen you have, you're going to take the crucible, lid, and white solid that now has the oxygen, minus the crucible and lid and magnesium, because this is before you added it into the flame. So you subtract that, you get 0.029 as the mass of oxygen. You convert that to moles, and you get 0.001. Now to find empirical formula, you're going to divide by the least number of moles. Since the number of moles is the same, it's pretty much 1-to-1 ratio. The formula would be 1-to-1 or MgO, 1 Mg and 1 O. So if you were to actually do this lab in the classroom, there are a couple of errors you might occur. Well, first of all, the magnesium weighed might not all be pure magnesium. Maybe when you put the magnesium into the flame, not all the magnesium reacted. You may lose some of the magnesium, and then when you go to weigh it, you're not going to get an accurate reading. Maybe you have some impurities, so the products weren't just MgO. There's also some nitrogen in the air, so maybe some magnesium nitride formed, not just magnesium oxide. We're assuming that this magnesium strip is only reacting with oxygen in the air when we're burning it. You could modify your procedure to try to eliminate some of the errors. So modification would include taking the reacted magnesium nitride, reacting it with water to form ammonia, and additional MgO product may be formed to try to increase your yield. This is another example of lab data that's obtained where we want to try to figure out what the empirical formula of the compound is. So in this problem, they're telling you the mass of a sample. And what they want to know is the sample contains carbon, hydrogen, and oxygen. We need to figure out what the empirical formula is of this compound. We are given data about the mass of the products produced. So we're told that the CO2, which is one of the products produced, is 1.039 grams, and water is 0.6369 grams. So what we're going to do is we're going to take the products given, and they're given in gram values, and we're going to convert those grams to moles. Once we know the moles of each of those, we can convert them into moles of atoms, and then we can convert them into grams. So we're given the mass of CO2, we want to convert that into moles of CO2, then to atoms of CO2. Same thing for when we're looking at our water. We want to convert this into moles of water, then moles of hydrogen atoms, then grams of hydrogen atoms. And the reason we're doing that is both of these have oxygen in them, so it's hard to do it with oxygen. What we're going to do is then take our original value, and we're going to subtract out the grams of the hydrogen and the carbon, and then whatever we're left with will be the amount of oxygen. Once we get the amount of oxygen in grams, we can convert that to moles. The idea here is we need to know the moles of carbon, hydrogen, and oxygen. We need to know the moles of each so that we can divide by the least number of moles. So we're trying to figure out what would be a way for us to figure out the moles of each. And since we're only given these gram values of compound, first we have to go to moles, then to atoms, and then to grams. So we'll show you the progression. We start with our grams of CO2. We're using dimensional analysis here. We convert to moles of CO2. This is 0.2361 moles of CO2, which we're then going to convert to atoms of CO2. Same thing for water. We're going to take our grams of water, convert it to moles of water, and then multiply by 2 because there are 2 hydrogen atoms. So right now, from the products, we're able to figure out how many moles of each we have. Next, we have to convert those moles into grams. So we figure out that we have 0.2836 grams by just doing your mole to gram conversion. And we're looking at moles of hydrogen, and we convert that to grams, so we figure out how many grams of hydrogen we have. So to figure out the oxygen, what we're going to do is take our original compound mass, and we're going to subtract the amount of carbon and hydrogen in the compound, so we get 0.188 grams of oxygen. Once we know the grams of oxygen, we can go to moles of oxygen. So we have 16 grams per mole in oxygen, so here's our value of oxygen. Next, what you do is you divide by the least number of moles. So just like we've done for all our empirical formulas, and it gives us a ratio of carbon to hydrogen to oxygen is carbon 2, hydrogen 6, oxygen 1. So at the end of this video, what we need to make sure that we understand is the interconversion of percent comp by mass to empirical formula. So when we're given percent composition, how to find the empirical formula. We need to know how to go from the molecular formula to its empirical formula. and we need to know how to use data when we're given to try to determine what the empirical formula is.